Imagine taking Mount Everest, all its rock, all its weight, and crushing it down until it fits into a single sugar cube. Now imagine holding that cube in your hand. It sounds impossible. It sounds like science fiction. But here is the shocking truth. Even that sugar cube would still be less dense than the matter inside a neutron star. This is not a story from a movie. This is not a theory meant only for textbooks. Neutron stars are real objects in our universe, quietly existing right now, scattered across the Milky Way. They're born from dead stars left behind after some of the most violent explosions the universe has ever seen. They are small, dark, and easy to miss, but in terms of raw extremes, they may be the most intense objects nature has ever created. When most people hear about extreme objects in space, they think of black holes. Black holes have a powerful reputation, and for good reason. But neutron stars are strange in a different way. A black hole hides its secrets behind an invisible boundary. A neutron star does not. It is a solid object with a surface spinning faster than anything you can imagine, wrapped in magnetic fields so strong they can tear atoms apart from thousands of kilometers away. In some ways, neutron stars push the laws of physics even harder than black holes do. A neutron star is not large. Many of them are only about the size of a city, yet they contain more mass than our sun, squeezed into that tiny space. Gravity on their surface is so strong that if you were somehow placed there, your body would be flattened instantly, stretched thinner than paper. Time itself behaves differently near them. Light bends, matter changes. The rules we rely on in everyday life simply stop working. And yet, these objects are not rare accidents. They are part of the natural life cycle of stars. The universe creates them again and again, as if testing just how far matter can be pushed before it completely collapses. In this video, we are going to explore neutron stars from the ground up, step by step, in simple language. We will see how they are born, what they're made of, and why they spin so fast. We will explore their crushing gravity, their violent magnetic fields, and their strange signals that blink across the universe like cosmic lighthouses. We will talk about what happens when two neutron stars collide, why those collisions created the gold on Earth, and how scientists detect these invisible monsters from thousands of light years away. By the end of this journey, you will understand why neutron stars are not just strange objects in space, but natural laboratories where the universe tests its most extreme limits. You will see why studying them helps us understand matter, gravity, time, and even our own existence. So take a deep breath, leave Earth behind, and let's begin by answering the most important question of all. What exactly is a neutron star? A neutron star is one of the most extreme and difficult objects in the universe to imagine, yet its basic idea is surprisingly simple. A neutron star is the collapsed core of a massive star that has died. It is what remains after a star far larger than our sun runs out of fuel, explodes, and then crushes itself inward under its own gravity. What is left behind is not a glowing ball of gas like the stars we see in the sky, and it is not a mysterious hole that swallows everything like a black hole. It is something in between. It is a real, solid object made of matter pushed to its absolute limit, where atoms are crushed so tightly that they lose their normal structure. In a neutron star, matter is packed in the most extreme stable form known to science. To understand what makes a neutron star special, it helps to first understand what it is not. A neutron star is not a normal star. When we look up at the night sky and see stars twinkling, we are seeing huge balls of hot gas that are alive with energy. These stars shine because deep inside their cores, atoms are constantly smashing together in nuclear reactions. This process releases enormous amounts of energy in the form of light and heat. Our sun is doing this right now. Every second, it converts hydrogen into helium and releases energy that warms Earth and makes life possible. A neutron star does none of this. It does not burn fuel. It does not produce energy through fusion. Its main life is already over. In that sense, calling it a star is slightly misleading. A neutron star is better described as the dense, dead heart of a star, the final object left behind after the star's active life has ended. When a massive star dies, it does not fade away quietly. Instead, it ends its life in one of the most violent events in the universe, a supernova explosion. During this explosion, the outer layers of the star are blasted into space, while the core collapses inward at incredible speed. Gravity becomes so powerful that it overwhelms every force trying to resist it. Electrons and protons are squeezed together, merging to form neutrons. This process happens so quickly and so violently that matter is transformed into something entirely new. The result is a neutron star, an object made almost entirely of neutrons, packed together with almost no empty space between them. One of the most shocking things about a neutron star is its size. In everyday life, we are used to associating heavy objects with large size. A mountain is heavy because it is big. A planet is heavy because it is enormous. A neutron star completely breaks this expectation. Most neutron stars are only about 20 kilometers wide. That is roughly the size of a large city. If you placed a neutron star on Earth, it would fit comfortably within the boundaries of a city like Mumbai, London, or New York. Some neutron stars are even smaller, closer to the size of a medium-sized town. Compared to Earth, which has a diameter of more than 12,000 kilometers, a neutron star is incredibly tiny. If Earth were the size of a football stadium, a neutron star would be smaller than a grain of sand. Yet despite this tiny size, a neutron star contains an almost unbelievable amount of mass. Most neutron stars have a mass that is greater than the mass of our Sun. The Sun is so large that over 1 million Earths could fit inside it. It is a massive, blazing sphere of gas stretching across 1.4 million kilometers. And yet, a neutron star, only a few dozen kilometers across, can weigh more than this enormous star. This means that all that mass has been squeezed into a space millions of times smaller. The result is a level of density that is almost impossible to visualize. To get a sense of this density, imagine taking the mass of Mount Everest and compressing it into a sugar cube. Now imagine doing that not just once, but over and over again, until an entire city-sized object is made of matter crushed this tightly. Scientists estimate that a single teaspoon of neutron star material would weigh billions of tons on Earth. It would punch straight through the ground, through the planet's crust, and sink toward the center of Earth like a bullet. This is not because the material is magical, but because gravity inside a neutron star forces matter into a state far denser than anything we can create or observe on our planet. This extreme density gives neutron stars their incredible gravity. Gravity on the surface of a neutron star is billions of times stronger than gravity on Earth. If you are somehow able to stand on the surface of a neutron star, which is purely hypothetical, your body would not simply be crushed. It would be flattened and stretched at the same time, pulled into the star so strongly that individual atoms would be torn apart. Even light, which normally travels freely through space, is strongly bent near a neutron star. Looking at one would distort your view of the universe behind it, as gravity curves space itself. Because neutron stars are so different from normal stars, scientists often describe them as cosmic leftovers. This phrase captures their true nature. A neutron star is not something the universe sets out to create directly. It is what is left behind after something else has finished its life. Just as ashes are left after a fire burns out, a neutron star is left after a massive star has burned through all its fuel and exploded. It is the final stable form that matter can take when gravity wins but does not quite go far enough to create a black hole. If the collapsing core of a star is slightly more massive, gravity will crush it even further and form a black hole. If it is slightly less massive, it settles into the form of a neutron star. In this way, neutron stars sit at a delicate boundary between existence and disappearance. Despite being leftovers, neutron stars are anything but boring. They are some of the most active and powerful objects in the universe. Many of them spin at incredible speeds, rotating dozens or even hundreds of times every second. Some emit intense beams of radiation that sweep across space like lighthouse beams, flashing with clock-like precision. Others possess magnetic fields so strong that they can rip atoms apart from thousands of kilometers away. These behaviors all come from the same basic cause: extreme mass packed into an incredibly small space. To build a clear mental picture of a neutron star, imagine this. Take the mass of the Sun, compress it until it fits inside a sphere no larger than a city. Remove all the empty space inside atoms, forcing particles together until they touch. Then spin this object faster and faster, faster than a kitchen blender, faster than a jet engine, until it becomes a rapidly rotating cosmic bullet. Wrap it in gravity so strong that even light struggles to escape, and surround it with invisible magnetic forces powerful enough to reshape matter. That object, strange as it sounds, is a neutron star. Neutron stars remind us that the universe does not care about human intuition. They exist in a realm where everyday rules no longer apply. Size does not match weight. Solid matter behaves like something alien. Time and space bend under pressure. And yet neutron stars are not imaginary. They are real objects that astronomers observe, measure, and study. They are scattered throughout our galaxy, silently spinning in the darkness, carrying within them the story of stars that lived fast, died violently, and left behind one of the most extreme objects nature can create. Understanding what a neutron star is at its most basic level is the first step in understanding why they matter so much to science. They are not just strange objects floating in space. They are natural experiments created by the universe itself, showing us what happens when matter is pushed to its absolute limits. And now that we know what a neutron star truly is, we can begin to explore how such an object is born and what incredible events lead to its creation. Before a neutron star can exist, there must first be a living star, and that story begins in one of the quietest places in the universe. Long before explosions, gravity, and violence, stars are born in vast clouds of gas and dust, drifting slowly through space. These clouds are cold, dark, and enormous, stretching across many light years. They look empty, but they are full of raw material. Hydrogen gas dominates these regions, mixed with small amounts of helium and heavier elements left behind by earlier generations of stars. For millions of years, nothing seems to happen. Then slowly and almost gently, gravity begins to pull the cloud inward. As gravity acts, parts of the gas cloud start to clump together. These clumps grow denser and heavier, pulling in more material from their surroundings. Over time, a dense core forms at the center of the cloud. As more gas falls inward, the core heats up. This heating happens not because of fire, but because of pressure. Gravity squeezes the gas tighter and tighter, raising the temperature higher and higher. Eventually, the core becomes so hot and dense that a critical moment is reached. Nuclear reactions ignite. At that instant, a star is born. This process is not dramatic or explosive at first. A newborn star begins its life quietly, hidden inside the leftover gas and dust of its birth cloud. Once nuclear fusion starts, the star enters a long and stable phase of its life. Fusion is the engine that powers all normal stars. In the core, hydrogen atoms smash together under extreme heat and pressure and fuse to form helium. When this happens, a tiny amount of mass is converted into energy. That energy moves outward, creating heat and light. This is what makes stars shine. The key to a star's stability lies in a delicate balance between two opposing forces. On one side is gravity, constantly trying to pull all the star's material inward, collapsing it into a smaller and smaller space. On the other side is pressure, produced by the energy released from nuclear fusion. This pressure pushes outward, trying to make the star expand. As long as these two forces are balanced, the star remains stable. It neither collapses nor explodes. Our Sun is in this balanced state right now, and it will remain that way for billions of years. However, not all stars are the same. Some are small, like red dwarfs, and burn their fuel slowly. Others, like the Sun, are medium-sized and live long, steady lives. But a small number of stars are born massive, many times heavier than the Sun. These massive stars live fast and dangerous lives. They burn through their fuel at an incredible rate, shining brighter and hotter than smaller stars. While the Sun will live for around 10 billion years, a very massive star may live for only a few million years. In cosmic terms, that is a blink of an eye. Only these massive stars can become neutron stars. The reason is simple but profound. Creating a neutron star requires gravity strong enough to crush matter beyond normal limits. Smaller stars do not have enough mass. When a star like the Sun reaches the end of its life, it gently sheds its outer layers and leaves behind a white dwarf, a dense but relatively calm object. There is no violent collapse. Gravity is not strong enough to push matter any further. Massive stars, however, are different. Their enormous weight gives gravity the upper hand when the fuel runs out. As a massive star ages, it begins to change internally. Hydrogen in the core slowly runs out. When this happens, fusion does not stop immediately. Instead, the star begins fusing heavier elements. Helium fuses into carbon, carbon into oxygen, oxygen into neon, and so on. Each new stage of fusion produces energy, but each stage is shorter than the last. The star becomes layered like an onion, with different elements fusing in shells around the core. The core itself becomes heavier and denser with each stage. There is a crucial limit here. Fusion can produce energy only up to a certain point. When the core fills with iron, everything changes. Iron is special because fusing iron does not release energy. Instead, it consumes energy. At this moment, the star loses its main source of outward pressure. The delicate balance that kept the star stable for millions of years begins to fail. Gravity does not wait. As soon as fusion can no longer push outward strongly enough, the star's core begins to collapse. This collapse is sudden and unstoppable. In a fraction of a second, the core falls inward at a significant fraction of the speed of light. The pressure and temperature skyrocket. Electrons are forced into protons, creating neutrons and releasing floods of particles. The core shrinks rapidly, becoming unimaginably dense. This is the moment when the life of the star turns violent. The outer layers of the star, which were still falling inward, crash into the suddenly hardened core and rebound outward in a catastrophic explosion. This explosion is a supernova, one of the brightest and most powerful events in the universe. For a brief time, a single star can outshine an entire galaxy. Heavy elements are forged and scattered into space, seeding future stars, planets, and even life. What remains at the center after this explosion depends entirely on the star's original mass. If the core is too light, it becomes a white dwarf. If it is too heavy, gravity crushes it into a black hole. But if the mass is just right, gravity compresses the core until it reaches a new kind of balance. This balance is not between fusion and gravity, but between gravity and the resistance of neutrons packed together as tightly as nature allows. The result is a neutron star. Understanding the life of a star before death is essential to understanding neutron stars. Neutron stars are not random objects. They are the inevitable outcome of a star that was born massive, lived fast, burned fiercely, and died violently. Every neutron star carries within it the history of its parent star, from the quiet gas cloud where it formed to the explosive moment that ended its life. This long build-up, from calm birth to catastrophic collapse, sets the stage for everything that makes neutron stars so extreme. Their density, gravity, spin, and magnetic fields are all consequences of this life story. To understand why neutron stars behave the way they do, we must remember that they are born not in peace, but in chaos. And now that we have seen how a star lives and why massive stars are destined for a dramatic end, we are ready to look closely at the exact moment when gravity wins completely and a neutron star is born. A supernova is often described as a giant explosion in space, but that description only captures a small part of what really happens. A supernova is not just an explosion, it is the violent end of a massive star's life, a moment when gravity finally wins a long battle that has lasted millions of years. It is the instant when a star can no longer hold itself up, when its own weight becomes too much, and when the laws of physics are pushed to their breaking point. Without supernova, neutron stars would not exist. Every neutron star begins its life inside this single, catastrophic event. To understand what a supernova really is, it helps to remember how a massive star survives in the first place. For most of its life, a star exists in balance. Gravity pulls everything inward, trying to crush the star. At the same time, energy from nuclear fusion pushes outward, holding the star up. This balance is not calm or gentle. It is a constant struggle. As long as the star can keep producing energy in its core, it can resist gravity. But when that energy production stops, gravity does not slowly take over. It collapses the star suddenly and brutally. In a massive star, the end begins when the core fills with iron. Unlike lighter elements, iron cannot produce energy through fusion. When iron builds up, the core becomes like a heavy engine that no longer works. Fusion slows, then stops. The outward pressure that held gravity back begins to disappear. For a short time, the star may still look normal from the outside, but deep inside, disaster has already begun. Once fusion fails, gravity takes control completely. The core of the star starts collapsing inward under its own enormous weight. This collapse is not slow. It happens in less than a second. The core, which may be thousands of kilometers wide, begins to shrink rapidly. Matter falls inward at incredible speeds, approaching a significant fraction of the speed of light. Temperatures rise to billions of degrees. Pressures become so extreme that atoms can no longer survive in their normal form. As the collapse continues, electrons are forced into protons. This is not a choice. Gravity squeezes matter so tightly that the particles have nowhere else to go. When electrons and protons combine, they form neutrons and release tiny particles called neutrinos. In this moment, the core of the star is transforming into something entirely new. It is becoming a neutron-rich object, the foundation of a future neutron star. Then comes a critical moment. The core reaches a point where it can no longer be compressed easily. Neutrons are packed together so tightly that they begin to resist further collapse. This resistance is not due to heat or fusion, but due to the fundamental properties of matter itself. The core suddenly stiffens. Meanwhile, the outer layers of the star are still falling inward at tremendous speed. When these infalling layers slam into the newly hardened core, they rebound violently. This rebound sends a powerful shockwave racing outward through the star. In a fraction of a second, the shockwave tears through the stellar material, ripping the star apart from the inside. This is the moment we see as a supernova explosion. The star's outer layers are blasted into space at thousands of kilometers per second. The explosion releases more energy in a few seconds than the sun will produce in its entire lifetime. For a brief time, a single supernova can shine brighter than an entire galaxy containing hundreds of billions of stars. It can be seen from millions or even billions of light years away. But this brightness is only the visible surface of a deeper event. Most of the energy released during a supernova is not light at all. It is carried away by neutrinos, ghost-like particles that pass straight through matter. In fact, more than 99% of the energy of a supernova is released invisibly, making the explosion both incredibly powerful and strangely hidden. In the final seconds before the explosion, everything happens incredibly fast. The core collapses, rebounds, and stabilizes into a dense object just tens of kilometers across. Time seems almost irrelevant at this scale. Processes that would normally take millions of years happen in moments. The star does not have time to adjust or respond. Gravity forces an immediate outcome. What remains at the center after the explosion is the most important part of the story. If the collapsing core is within a certain mass range, gravity compresses it into a neutron star. The core becomes an object with more mass than the Sun, packed into a space no larger than a city. It is incredibly hot at first, glowing with leftover energy from its violent birth. Over time it cools, but it never returns to anything resembling a normal star. It is a new kind of object, born directly from the collapse. There are many myths surrounding supernova, especially in popular media. One common myth is that a supernova is simply a star exploding outward like a bomb. In reality, the explosion begins with an inward collapse, not an outward blast. Gravity pulls the star in before anything explodes outward. Another myth is that supernova destroy everything around them. While they're extremely powerful, they do not wipe out entire galaxies. In fact, supernovae are essential to creation. They spread heavy elements like carbon, oxygen, gold, and iron into space, making planets and life possible. Another misconception is that supernovae are rare accidents. In truth, they are a natural and expected part of the universe. Massive stars are born knowing how they will die. Every massive star is destined for a supernova. It is not a failure or a mistake. It is the final step of stellar evolution. It is also often imagined that supernovae last a long time, like slow-burning explosions. In reality, the core collapse itself happens in a blink. What we see as a glowing supernova can last weeks or months, but the critical moment that creates a neutron star happens almost instantly. The fate of the star is decided in seconds. Supernovae are not just dramatic endings, they are beginnings. Without them, neutron stars would not exist. Without them, black holes would not form. Without them, the elements needed for planets, oceans, and living cells would never spread through space. Every atom of iron in your blood and calcium in your bones was once forged or scattered by a supernova. When we look at a neutron star, we are looking at the frozen core of a catastrophe. Its density, gravity, spin, and magnetic fields are all consequences of the supernova that created it. The explosion is not something that happened around the neutron star. It is something that created the neutron star. Understanding supernova is essential because they show us how gravity truly wins. They reveal what happens when energy runs out and nature has no choice but to compress matter beyond imagination. They mark the exact moment when a star stops being a star and becomes something far stranger and more extreme. Now that we understand what a supernova really is, how the collapse happens step by step, and how gravity takes control in the final seconds, we are ready to look even deeper. Because once the explosion fades and the debris drifts away, what remains at the center is one of the most extreme objects in existence. The next step is to explore what happens to matter when it is crushed beyond atoms, and how a neutron star is truly born from the ashes of a dying star. The birth of a neutron star is not a gentle transition. It is one of the most violent and extreme transformations matter can experience in the universe. In the final moments after a supernova explosion begins, the core of the dying star is crushed inward with such force that the very structure of matter collapses. Atoms, which normally seem solid and stable, are mostly empty space. In everyday life, we never notice this emptiness because electromagnetic forces keep electrons in place around nuclei. But inside a collapsing stellar core, gravity becomes so overwhelming that it ignores these forces completely. The empty space inside atoms vanishes. Electrons are ripped away from their orbits and forced deep into atomic nuclei. The familiar idea of matter, with atoms arranged neatly like tiny solar systems, simply stops existing. As the collapse accelerates, pressure and density rise to unimaginable levels. Temperatures reach billions of degrees, but heat is no longer the most important factor. Gravity is. The core is being squeezed from all sides at nearly the speed of light. Electrons, which normally resist being pushed together, are compressed into protons. When this happens, a fundamental transformation takes place. An electron merges with a proton, and together they form a neutron. This process releases a flood of nearly invisible particles called neutrinos, which escape into space carrying away enormous amounts of energy. In just seconds, the core of the star changes from a place filled with atoms to a place filled almost entirely with neutrons. This is not chemistry. This is not ordinary nuclear physics. This is matter being rewritten at its deepest level. At this point, the star is no longer supported by fusion, heat, or electrical forces. Everything that once held matter apart has failed. Normal physics, the rules that govern everyday objects and even ordinary stars, breaks down. Gravity has forced matter into a state that cannot exist anywhere else in the universe, except under the most extreme conditions. Neutrons are packed so tightly together that there is almost no space between them. A teaspoon of this material would outweigh mountains. The density becomes comparable to that of an atomic nucleus, extended to the size of an entire city. The collapsing core is now something entirely new. It is becoming a neutron star. But here is the critical question. If gravity is this strong, why does the core stop collapsing at all? Why does it not continue inward and become a black hole? The answer lies in a subtle and powerful form of resistance that only appears at these extreme densities. Neutrons are not just neutral particles. They follow strict quantum rules that prevent them from being packed infinitely close together. As the neutrons are squeezed tighter and tighter, they begin to push back. This resistance, known as neutron pressure, is not caused by heat or fusion. It is a fundamental property of matter itself. It represents the last line of defense against gravity. When the collapsing core reaches this limit, something extraordinary happens. The inward fall of matter suddenly slows and then stops. The core stiffens almost instantly, forming a solid object with a defined surface. Meanwhile, the outer layers of the star, still falling inward from the collapse, crash into this newly formed neutron core. The impact sends a shockwave outward, contributing to the supernova explosion that tears the rest of the star apart. At the center, the neutron star is born, incredibly hot, incredibly dense, and spinning rapidly due to the conservation of angular momentum. This moment is the true birth of a neutron star. It is not a slow formation over time. It happens in seconds. One moment, the core is collapsing matter. The next, it is a compact object only tens of kilometers wide, containing more mass than the Sun. The transformation is so fast that the universe barely has time to react. Energy pours out in the form of neutrinos. Space-time itself shudders under the sudden change in mass distribution. The newborn neutron star emerges from chaos, forged under conditions more extreme than anywhere else outside a black hole. The reason the star does not become a black hole is a matter of balance. If the collapsing core has just the right mass, neutron pressure can stop gravity at the last possible moment. The core settles into a stable configuration, neither expanding nor collapsing further. But this balance is fragile. If the core is only slightly more massive, gravity overwhelms neutron pressure, and the collapse continues, forming a black hole. If it is slightly less massive, the neutron star remains stable for billions of years. Neutron stars exist on a narrow boundary between existence and disappearance. between something and nothing. The newborn neutron star is far from calm. It is spinning at incredible speed, sometimes rotating dozens or even hundreds of times per second. Its magnetic field, inherited and intensified from the original star, becomes unimaginably strong. The surface temperature is millions of degrees, glowing intensely in X-rays. Over time, the neutron star cools and quiets, but it never becomes ordinary. It remains a compact extreme object, carrying within it the memory of its violent birth. To imagine this birth clearly, picture the core of a massive star collapsing inward faster than any explosion outward. Picture atoms being crushed flat, their internal space erased. Picture electrons vanishing into protons, rewriting matter into neutrons. Picture gravity pushing until it finally meets resistance at the deepest level of reality. Then, in a sudden moment, the collapse halts. The universe draws a line and says no further. A neutron star is born. This birth is not just an astronomical event. It is a demonstration of the ultimate limits of matter. It shows us how the universe behaves when pushed beyond familiar conditions. Neutron stars are not theoretical curiosities. They are real objects, created by nature in moments of unimaginable violence, and left behind as enduring monuments to gravity's power. Every neutron star we observe today is the frozen remnant of this dramatic moment. Its density, its gravity, its spin, and its magnetic field all trace back to the instant when matter was crushed beyond imagination and yet did not vanish into a black hole. Understanding this birth helps us understand why neutron stars are so extreme, so mysterious, and so important to science. And now that we have witnessed how a neutron star is born, we can begin to explore what living with such extreme gravity and density truly means, and how these objects behave long after the explosion fades and the universe grows quiet again. Trying to understand the size, mass, and density of a neutron star is where human intuition completely fails. Our brains are built to understand everyday objects. We understand cars, buildings, mountains, and planets because we experience size and weight every day. Neutron stars exist far outside this comfort zone. They are not just extreme, they are so extreme that normal comparisons stop working and numbers begin to lose their meaning. To truly understand a neutron star, we must rebuild our sense of scale from the ground up. Let's begin with size because this is where the shock first hits. When people imagine something heavier than the sun, they naturally picture something enormous. But a neutron star is the opposite. Most neutron stars are only about 20 kilometers wide. That is it. If you were flying in an airplane at cruising altitude, you could cross a neutron star from one side to the other in less than 2 minutes. Place a neutron star on Earth, and it would fit entirely inside a major city. You could place it where a city like Delhi, London, or New York sits, and there would still be space left over. Compared to Earth's diameter of more than 12,000 kilometers, a neutron star is unbelievably small. If Earth were the size of a football stadium, a neutron star would be smaller than a marble. Now comes the part that breaks logic. Despite being city-sized, a neutron star contains more mass than the Sun. The Sun is so large that over 1 million Earths could fit inside it. It dominates our solar system with its gravity and light. And yet, a neutron star, no larger than a city, can outweigh it. Imagine taking the entire Sun and crushing it down until it fits inside a space the size of a city. That is not a metaphor. That is literally what has happened. All that mass is squeezed into an incredibly tiny volume. This leads directly to density, the most mind-bending property of neutron stars. Density is simply how much mass is packed into a given space. On Earth, even the densest materials like iron or lead are mostly empty space at the atomic level. A neutron star is different. Matter inside a neutron star is packed so tightly that atoms no longer exist. The empty space inside atoms is gone. What remains is matter compressed almost to the density of an atomic nucleus. To understand this, scientists often use a famous example. Imagine taking 1 teaspoon of neutron star material and placing it on Earth. That single teaspoon would weigh billions of tons. It would weigh more than Mount Everest. It would weigh more than all the buildings in a major city combined. There is nothing on Earth that can support such weight. The spoon would fall straight through the ground, through the crust, through the mantle, and toward Earth's core, not because it is sharp or fast, but because gravity would pull that mass downward with unstoppable force. Another way to picture this density is to imagine compressing the entire human population of Earth into the size of a sugar cube. Now imagine doing that not with people, but with mountains, oceans, and continents over and over again, until a city-sized object contains more mass than a star. That is the level of compression we are talking about. At this point, numbers stop helping. Only imagination can get us close. This extreme density creates gravity unlike anything we experience. Gravity on Earth feels gentle because Earth is large and spread out. Even though Earth is massive, its mass is distributed over a wide area. A neutron star concentrates its mass into a tiny space, and gravity responds accordingly. On the surface of a neutron star, gravity is billions of times stronger than Earth's gravity. To understand what this means in daily life terms, imagine standing on Earth holding a backpack. That backpack pulls downward with a certain weight. Now imagine that weight suddenly becomes billions of times heavier. Your bones would not break, your body would not simply collapse. You would be flattened instantly, crushed thinner than a sheet of paper. Your atoms would be pulled apart, stretched and compressed at the same time. Gravity would not give your body time to react. This is why standing on a neutron star is impossible, even in theory. The surface gravity is so strong that the difference in gravity between your head and your feet would be extreme. This difference is called tidal force. On Earth, tidal forces are weak. On a neutron star, they are deadly. Your feet would be pulled far more strongly than your head, stretching your body vertically while crushing it downward. Long before you touch the surface, you would be torn apart at the atomic level. Even light struggles near a neutron star. Light normally travels in straight lines through space, but near a neutron star, gravity bends space itself. Light curves as it passes by. If you could see a neutron star directly, you would not see a simple sphere. You would see a distorted view of the universe behind it, wrapped and bent by gravity. In some cases, you could even see parts of the neutron star's surface that should be hidden behind the horizon, because gravity bends the path of light around the star. The strength of gravity also affects time. Near a neutron star, time moves more slowly than it does far away. This effect, predicted by Einstein, is small on Earth, but significant near compact objects. A clock placed on the surface of a neutron star would tick more slowly than a clock in deep space. The star's gravity warps not only space, but time itself. To build a clear visual picture, imagine this scene. Picture a city floating alone in space, dark and silent. Now imagine that this city-sized object weighs more than the sun. Imagine gravity so strong that the city is wrapped in invisible force, crushing everything inward. The surface is solid, but nothing can stand on it. Light bends, time slows. Matter behaves in ways no human has ever experienced. That is what a neutron star looks like. It is important to understand that neutron stars are not just dense versions of normal objects. They are not planets turned heavy or stars turned small. They are a completely different state of matter. The rules we rely on for everyday materials no longer apply. Concepts like solid, liquid, and gas lose their meaning. Inside a neutron star, matter exists in forms that scientists are still trying to understand. This is why neutron stars are so valuable to science. They are natural laboratories where the universe shows us what happens when matter is pushed to its absolute limits. We cannot recreate these conditions on Earth. No machine, no experiment, no explosion can compress matter this much. Only gravity, acting on the scale of stars, can do this. When you hear numbers like 20 kilometers wide or billions of tons per teaspoon, it is easy to let them pass by without feeling their weight. But these numbers describe something real. Somewhere in our galaxy, there are objects the size of cities that outweigh stars, objects where gravity dominates reality itself. They are quiet most of the time, invisible to the naked eye, yet they are among the most extreme things that exist. Understanding the size, mass, and density of neutron stars prepares us for everything that comes next. Their incredible gravity explains why they spin so fast, why their magnetic fields are so strong, and why their behavior seems almost unreal. These numbers may not make sense at first, but they are the foundation of everything that makes neutron stars what they are. And once you truly grasp how small, heavy, and dense these objects are, you begin to understand why the universe treats them with such power and respect. Gravity on Earth feels familiar and gentle. It keeps us grounded, pulls objects downward, and gives weight to everything around us. We barely think about it because it's constant and predictable. But gravity is not the same everywhere in the universe. On a neutron star, gravity reaches a level so extreme that it no longer feels like a force pulling things down. It becomes something that reshapes reality itself. Space bends, time slows, light curves. The rules that make sense in daily life simply stop working. To understand how extreme neutron star gravity is, let's start with a simple comparison. Earth's gravity is strong enough to hold oceans, mountains, and an atmosphere, but it is still weak on a cosmic scale. If you drop a stone on Earth, it falls gently. On a neutron star, gravity is billions of times stronger. This means that if Earth's gravity were scaled up to match a neutron star's, you would weigh more than a mountain. Your body would not feel heavy. It would feel impossible. Even the strongest materials we know would behave like soft clay under such force. This immense gravity exists because of how tightly a neutron star's mass is packed. Remember, a neutron star has more mass than the Sun, squeezed into a space no larger than a city. Gravity depends on mass and distance. When massive amounts of matter are concentrated into a tiny area, gravity becomes overwhelming. On the surface of a neutron star, the pull downward is so intense that falling just a few centimeters would accelerate you to incredible speeds. There is no gentle landing. There is no balance. One of the most fascinating effects of this gravity is how it bends light. Light normally travels in straight lines through space. That is why we can see distant stars clearly. But according to Einstein's theory of gravity, massive objects curve space itself. Light follows the curves of space, not straight paths. Near a neutron star, this curvature becomes extreme. Light passing close to the surface is bent sharply, wrapping around the star. This means something very strange for an observer. If you could look at a neutron star, you would see more than half of its surface at once. Light from the far side of the star would be bent around toward you. The neutron star would appear distorted, almost like a warped mirror of the universe behind it. This bending of light is not a visual trick, it is gravity reshaping the paths that light must follow. Gravity near a neutron star also affects time itself. On Earth, time feels constant. 1 second always feels like 1 second, but time is not absolute. Strong gravity slows the passage of time. This effect is tiny on Earth, but near a neutron star, it becomes significant. A clock placed on the surface of a neutron star would tick noticeably slower than a clock far away in space. This means that if you could somehow survive near a neutron star, time for you would pass more slowly, compared to someone watching from a distance. This time slowing is not science fiction. It is a real effect confirmed by experiments and observations. Gravity changes how fast time flows. Near a neutron star, Time stretches, just as space bends. The stronger the gravity, the greater the effect. Neutron stars exist in a region where these effects are no longer subtle. They are part of everyday reality for the star. Now imagine what it would feel like to fall toward a neutron star. This is where human imagination truly breaks down. On Earth, falling is familiar. You accelerate gently, reach a modest speed, and hit the ground. Near a neutron star, the fall would be brutal. Long before you reach the surface, gravity would pull you faster and faster. Within a very short distance, you would be moving at a significant fraction of the speed of light. As you fall, gravity would not pull evenly on your body. The pull on your feet would be much stronger than the pull on your head. This difference is called tidal force. On Earth, tidal forces are weak and mostly noticeable in ocean tides. Near a neutron star, tidal forces are deadly. Your body would be stretched vertically while being crushed downward. This process is sometimes called spaghettification, but near a neutron star, even that word feels too gentle. You would be torn apart at the atomic level before ever reaching the surface. If somehow you are immune to this stretching and manage to reach the surface intact, the result would be immediate destruction. The surface gravity is so intense that the moment you touched it, you would be flattened into a layer thinner than an atom. There would be no pain, no awareness. Physics would end your existence instantly. This is why standing on a neutron star is not just impossible in practice. It is impossible in principle. Escape from a neutron star is almost impossible as well. On Earth, you can escape gravity by reaching a speed of about 11 kilometers per second. Rockets can do this. On a neutron star, the escape speed is a significant fraction of the speed of light. Nothing made of ordinary matter could achieve this without being destroyed. Even light struggles. While neutron stars do not trap light completely like black holes do, light leaving their surface loses a large amount of energy climbing out of the gravitational well. This causes it to shift to lower energy, becoming redder and weaker. This is another sign that gravity near a neutron star warps reality. Energy itself is affected. Signals leaving the surface are stretched. Radiation is altered. Everything that tries to escape must fight against gravity's grip. This is why neutron stars appear faint despite their extreme nature. Their light is dragged down by gravity before it ever reaches us. What makes neutron star gravity especially fascinating is that it exists just below the threshold of a black hole. If the star were only slightly more massive, gravity would become strong enough to trap light completely. But neutron stars sit on the edge. They show us what gravity does just before it becomes absolute. They allow us to study extreme gravity without crossing into the unknowable interior of a black hole. To picture this clearly, imagine standing near a massive pit in the fabric of space. The deeper you go, the steeper the walls become. Near Earth, the slope is gentle. Near a neutron star, the slope becomes almost vertical. Climbing out requires enormous energy. Falling in happens instantly. Space itself curves downward toward the star, and everything follows that curve whether it wants to or not. Neutron stars teach us that gravity is not just about falling objects. It is about the shape of the universe. Near these objects, space is bent, time is stretched, and light is redirected. Reality behaves differently, not because of magic, but because gravity has reached an extreme. Understanding this gravity is essential to understanding everything else about neutron stars. Their rapid rotation, their intense magnetic fields, and their violent outbursts all depend on this crushing gravitational environment. Gravity is the reason neutron stars exist at all, and it is the force that defines every moment of their existence. As we move forward, this warped reality will explain why neutron stars behave like cosmic engines, spinning faster than anything else, emitting powerful beams of radiation, and influencing their surroundings in dramatic ways. Gravity is the foundation. Once you understand how extreme it is, everything else begins to make sense. One of the most astonishing features of neutron stars is how incredibly fast they spin. Rotation is something we see everywhere in the universe. Planets rotate, stars rotate, galaxies rotate. Even Earth spins once every 24 hours, giving us day and night. But neutron stars take this simple idea of rotation and push it to an extreme that feels almost unreal. Some neutron stars spin hundreds of times every second. Not per minute, not per hour, per second. At these speeds, the idea of a spinning star stops feeling familiar and starts feeling impossible. To understand why neutron stars spin so fast, we need to go back to their birth. Before becoming a neutron star, the object was the core of a massive star. That star was already rotating, slowly but steadily, just like most stars do. When the star exploded as a supernova, its core collapsed inward dramatically. What happened next follows one of the most important and simple rules of physics, a rule you can understand without equations. It is called conservation of angular momentum. Here is the easiest way to understand it. Imagine a figure skater spinning on ice. When the skater stretches their arms outward, they spin slowly. When they pull their arms inward, they spin much faster. Nothing magical happens. The skater does not add energy. The spin speeds up simply because the same amount of rotation is now concentrated into a smaller space. This rule applies everywhere in nature. The collapsing core of a star behaves exactly like that skater. Before collapse, the core is large, maybe thousands of kilometers wide, and rotating slowly. When gravity crushes it down into a neutron star only about 20 kilometers across, all that rotation is squeezed into a tiny object. The result is a dramatic increase in spin speed. What once took days or hours now takes milliseconds. This is why neutron stars spin so fast. They are not engines that turn themselves on. They are the result of rotation being conserved during collapse. The universe does not allow rotation to disappear. It only allows it to be concentrated. And neutron stars are rotation concentrated to the extreme. Some neutron stars rotate a few times per second. Others rotate dozens of times per second. But the most extreme ones, called millisecond pulsars, spin hundreds of times per second. The fastest known neutron stars rotate more than 700 times every second. That means the surface of the star is moving at a speed close to a significant fraction of the speed of light. No material object on Earth could survive such rotation. To truly grasp how extreme this is, imagine if Earth spun that fast. Right now, Earth rotates once every 24 hours. This speed is gentle. We do not feel it. If Earth rotated once every second, the result would be immediate disaster. Oceans would fly off into space. The atmosphere would be stripped away. Mountains would collapse. The planet would tear itself apart due to centrifugal forces. Now imagine Earth rotating hundreds of times per second. The planet would not remain a planet at all. It would be shredded instantly. The fact that neutron stars can rotate this fast without breaking apart tells us how incredibly strong gravity is inside them. Gravity on a neutron star is so powerful that it holds the star together even while it spins at speeds that would destroy any normal object. This extreme rotation has profound effects on how neutron stars behave. First, it affects their shape. Neutron stars are not perfect spheres. Fast rotation causes them to bulge slightly at the equator and flatten at the poles. The faster they spin, the more distorted they become. This distortion is small compared to their overall size, but it plays a crucial role in how they emit radiation. Rotation also plays a key role in the creation of pulsars, one of the most famous types of neutron stars. Many neutron stars emit beams of radiation from their magnetic poles. As the star spins, these beams sweep through space like the beam of a lighthouse. If Earth happens to lie in the path of one of these beams, we see regular flashes of light or radio waves. These flashes can be so precise that some pulsars rival atomic clocks in accuracy. Their rotation is so stable that scientists can predict their pulses years in advance. Spin also affects a neutron star's magnetic field. When a star collapses into a neutron star, its magnetic field is compressed along with everything else. Fast rotation twists and intensifies this field even further. The faster the spin, the more energetic the magnetic activity. This can lead to powerful radiation, sudden bursts of energy, and in extreme cases violent starquakes on the neutron star's surface. Over time, neutron stars can slow down. As they emit radiation and particles into space, they lose energy. This energy loss causes their rotation to gradually decrease. Some neutron stars spin down smoothly over millions of years. Others experience sudden changes called glitches, where their rotation speed jumps slightly. These glitches are thought to be caused by shifts inside the star, showing that even after birth, neutron stars are dynamic, evolving objects. There is another fascinating twist in this story. Some neutron stars spin fast not only because of their birth, but because they have been spun up later. In binary systems, where a neutron star orbits another star, material can be pulled from the companion star onto the neutron star. As this material falls in, it transfers angular momentum, speeding up the neutron star's rotation. This process can turn an ordinary neutron star into a millisecond pulsar, spinning hundreds of times per second long after its violent birth. Rotation also affects how neutron stars interact with their surroundings. A rapidly spinning neutron star can generate strong winds of particles and radiation, shaping the space around it. These winds can create glowing nebulae and shockwaves visible across vast distances. The star's spin becomes a source of power, driving cosmic activity long after fusion has ended. To visualize all of this, imagine a city-sized object spinning faster than a kitchen blender, faster than a jet turbine, faster than anything humans have ever built. Imagine its surface racing around at near light speed, held together only by gravity so strong it bends space and time. This is not an exaggeration. This is the daily reality of a neutron star. Rotation turns neutron stars into cosmic machines. It gives them rhythm. It gives them energy. It makes them visible across the galaxy. Without rotation, neutron stars would be far quieter and harder to detect. With rotation, they become some of the most precise and powerful objects in the universe. Understanding their spin helps us understand why neutron stars behave the way they do, why they flash, why they emit radiation, and why they remain stable despite their extreme conditions. Rotation is not just a detail, it is one of the defining features that makes neutron stars the extreme objects they are. As we move forward, this rapid spin will connect directly to even more astonishing features, especially their magnetic fields, which become twisted and amplified by rotation into forces so strong they challenge our understanding of physics itself. Magnetic fields are something we encounter every day, even if we rarely think about them. Earth has a magnetic field that guides compasses and shields us from harmful radiation from the sun. A simple fridge magnet sticks to metal because of magnetic forces at work. These fields are invisible, but their effects are very real. In space, magnetic fields play an even bigger role. They shape stars, guide charged particles, and control powerful cosmic events. Yet even the strongest magnetic fields we know on Earth are nothing compared to the magnetic fields found around certain neutron stars. In that extreme environment, magnetism becomes one of the most violent and destructive forces in the universe. A magnetic field is created when electric charges move. In simple terms, whenever charged particles, like electrons, flow or spin, they generate magnetism. In stars, huge amounts of charged particles are constantly moving, so magnetic fields naturally form. In normal stars like the Sun, these fields are strong enough to create sunspots and solar flares. But when a star collapses into a neutron star, everything changes. The star's magnetic field is not destroyed. Instead, it is compressed, squeezed into a much smaller space, just like rotation and gravity. The result is a magnetic field amplified to terrifying levels. Some neutron stars possess magnetic fields so strong that scientists give them a special name: magnetars. Magnetars are not a different kind of object. They are neutron stars with magnetic fields pushed to the absolute extreme. While a typical neutron star already has a magnetic field trillions of times stronger than Earth's, a magnetar's field can be thousands of times stronger than that. These are the strongest magnetic fields ever observed in the universe. To understand how strong this really is, we need comparisons, even though no comparison truly works. Earth's magnetic field is gentle. It is just strong enough to protect our atmosphere and guide navigation. A powerful hospital MRI machine produces a magnetic field strong enough to affect metal objects and human tissue. But even that is still weak compared to a neutron star. A typical neutron star's magnetic field is about 1 trillion times stronger than Earth's. A magnetar's magnetic field can be 1,000 trillion times stronger than Earth's. These numbers are so large that they stop feeling real, but their effects are very real. In a magnetar, magnetism becomes more powerful than chemistry, stronger than molecular bonds, and even capable of affecting atomic structure. At close distances, the magnetic field is so intense that it would rip electrons away from atoms, tearing matter apart piece by piece. Solid objects would not remain solid. They would be stretched, twisted, and reshaped by invisible forces. Even empty space behaves differently in such fields, becoming unstable and reactive. If you were somehow brought close to a magnetar long before gravity or radiation could kill you, the magnetic field would. At a distance of thousands of kilometers, the field would already begin to interfere with the atoms in your body. Molecules would distort, chemical bonds would weaken. At closer range, the magnetic field would rearrange the electrons in your atoms, effectively pulling your body apart at the microscopic level. Your blood, bones, and tissues would lose their structure. There would be no pain, no sensation. The laws of biology would simply stop applying. Magnetars are dangerous not only up close but also from great distances. Their magnetic fields twist and strain the solid crust of the neutron star itself. Remember, a neutron star has a rigid surface, more like a solid than a gas. In a magnetar, the magnetic field becomes so intense that it can crack this crust, causing what scientists call starquakes. These are similar to earthquakes, but vastly more powerful. When a starquake happens, enormous amounts of energy are released in the form of gamma rays and X-rays. These outbursts are called magnetar flares, and they are among the most energetic events ever observed in our galaxy. In a single fraction of a second, a magnetar can release more energy than the sun produces in hundreds of thousands of years. These flares travel across space at the speed of light, spreading intense radiation far beyond the star itself. There have been real events caused by magnetars that scientists have observed from Earth. In 2004, a magnetar located about 50,000 light-years away released a massive flare. Even at that enormous distance, the burst was so powerful that it affected Earth's upper atmosphere. Satellites detected the signal, and some instruments were temporarily overwhelmed by the intensity. If such a flare occurred closer to Earth, it could seriously damage satellites, disrupt communications, and potentially affect life. What makes magnetars even more fascinating is that their magnetic fields slowly decay over time. As the magnetic field twists and breaks the crust, energy is released again and again. This decay is what powers magnetars. Unlike normal stars, magnetars do not rely on fusion. Unlike pulsars, they are not powered mainly by rotation. Magnetars are powered by magnetic energy itself. Their magnetism is so extreme that it becomes a fuel source. The presence of such intense magnetic fields also affects how light behaves near the star. In magnetar environments, light can split into different paths, a strange effect predicted by quantum physics. Space itself becomes a strange medium where light and energy behave in unfamiliar ways. Magnetars give scientists a rare opportunity to observe physics that cannot be tested anywhere else. It is important to understand that magnetars are not monsters by choice. They are the result of extreme conditions at birth. When a neutron star forms with rapid rotation and certain internal properties, its magnetic field can grow to unbelievable strength. Over time, that field becomes unstable, leading to the violent behavior we observe. Magnetars are rare, but their existence proves just how far nature can push physical laws. To picture a magnetar clearly, imagine a city-sized object floating in space, silent and dark. Around it is an invisible storm, a magnetic field so powerful that it reshapes matter itself. The surface of the star cracks and shifts under magnetic stress. Bursts of energy erupt without warning, sending lethal radiation across the galaxy. Nothing about this object is gentle. Nothing about it is safe. Magnetars remind us that magnetism is not just a quiet background force. Under the right conditions, it becomes one of the most destructive powers in the universe. These objects show us that neutron stars are not just dense and heavy, but also wildly energetic and unpredictable. Understanding magnetars helps us understand neutron stars as a whole. It reveals how gravity, rotation, and magnetism combine to create objects that feel almost unreal. These magnetic monsters push physics to its limits and give us a glimpse of how extreme the universe can truly be. And as we move forward, this magnetism will connect directly to one of the most fascinating behaviors of neutron stars: their ability to act like cosmic lighthouses, sending rhythmic signals across the universe with astonishing precision. When astronomers first detected pulsars, they did not know what they were looking at. The signals were so strange, so regular, and so precise that they seemed almost impossible to explain using known natural processes. They appeared as steady pulses of radio waves, arriving from deep space at perfectly even intervals. Tick, tick, tick. Some pulse once every second, others pulse dozens, or even hundreds of times per second. Nothing in nature was known to behave like that. For a brief moment in scientific history, some researchers seriously wondered whether they had discovered signs of intelligent life beyond Earth. These mysterious objects were later named pulsars, and today we know they are one of the most fascinating forms a neutron star can take. A pulsar is a rapidly rotating neutron star that emits beams of radiation from its magnetic poles. These beams do not shine in all directions. Instead, they shoot out into space like narrow cones. As the neutron star spins, these beams sweep across the universe. If Earth happens to lie in the path of one of these sweeping beams, we see a pulse of radiation each time it passes our way. This is why pulsars appear to blink. They are not turning on and off. They are rotating, and we are seeing their beams pass by us again and again. The lighthouse analogy is not just poetic, it is accurate. A lighthouse does not flash because the light itself is blinking. It flashes because the beam rotates and points toward you at regular intervals. Pulsars work the same way, but on a cosmic scale. A city-sized neutron star spins rapidly in space, and its intense magnetic field funnels radiation into focused beams. Each rotation sends a pulse outward. The faster the spin, the faster the pulses arrive. What makes pulsars truly remarkable is the precision of this blinking. Many pulsars are so regular that they rival atomic clocks in accuracy. Their pulses arrive with such stability that scientists can predict the timing years in advance. This precision comes from the incredible stability of neutron stars. Despite their violent birth and extreme conditions, once formed, they behave like cosmic flywheels, spinning steadily for millions or even billions of years. The discovery of pulsars happened in 1967, and it was completely unexpected. A young graduate student named Jocelyn Bell was analysing data from a radio telescope when she noticed a strange signal. It was a series of sharp radio pulses repeating with perfect regularity. At first, the signal was so unusual that it was labelled LGM, short for Little Green Men, as a joke reference to possible extraterrestrial origin. The idea of aliens was not taken seriously, but the regularity of the signal demanded an explanation. Soon, more signals like it were found in different parts of the sky. This ruled out the alien hypothesis. No civilization would build multiple transmitters across the galaxy, all sending the same kind of signal. Scientists realized they were witnessing a new natural phenomenon. The pulses were coming from rotating neutron stars, objects so extreme that their behavior had never been observed before. The reason pulsars are so regular lies in the physics of rotation and gravity. A neutron star is incredibly dense and compact. Once it starts spinning, there is very little to slow it down. There is no atmosphere, no weather, no internal turbulence like in a normal star. The star behaves more like a perfectly balanced spinning top in space. Unless acted on by an external force, it keeps spinning at almost the same rate. Some pulsars spin relatively slowly, taking seconds to complete one rotation. Others, known as millisecond pulsars, spin hundreds of times per second. These ultrafast pulsars are often found in binary systems, where they have been spun up by pulling material from a companion star. Each pulse we see is a direct result of this incredible rotation. The beams emitted by pulsars are powered by a combination of rotation and magnetic fields. As the neutron star spins, its magnetic field sweeps through space, accelerating charged particles to near-light speeds. These particles emit radiation across the electromagnetic spectrum, including radio waves, X-rays, and gamma rays. The exact type of radiation we detect depends on the pulsar and our viewing angle. Not all neutron stars are pulsars. A neutron star must have the right alignment of spin and magnetic field, and its beams must cross Earth's line of sight. Many neutron stars are invisible to us because their beams never point our way. Pulsars are special, not because they're rare, but because we are lucky enough to see them. Pulsars are incredibly useful to science. Because of their precision, they act as natural cosmic clocks. Scientists use them to test theories of gravity, including Einstein's predictions. Pulsars in binary systems allow researchers to study how space and time behave under extreme gravity. In some cases, pulsars have helped detect gravitational waves indirectly by revealing tiny changes in pulse timing. Pulsars are also used as navigation tools. Their predictable signals can serve as a kind of cosmic GPS, helping spacecraft determine their position in space. Future deep space missions may rely on pulsars for navigation far beyond Earth. The regularity of pulsars is so impressive that even tiny changes in their spin can be detected. Sometimes, a pulsar suddenly speeds up slightly in an event called a glitch. These glitches provide clues about the star's interior, suggesting that different layers inside the neutron star can rotate at slightly different speeds. In this way, pulsars allow scientists to probe the internal structure of objects that cannot be touched or directly observed. To visualize a pulsar, imagine a city-sized object spinning faster than a jet engine, surrounded by invisible magnetic forces. From its poles, beams of energy shoot out like searchlights, sweeping across the darkness of space. Every time one of those beams crosses Earth, our instruments detect a pulse. These pulses have been traveling for thousands or millions of years, crossing empty space with incredible consistency, only to arrive at our planet with perfect timing. What makes pulsars so captivating is not just their behavior, but what they represent. They are the remains of dead stars, transformed into precision instruments by gravity and physics. They turn chaos into order. From the wreckage of a supernova, the universe creates objects that tick with the reliability of clocks. Pulsars show us that, even in the most extreme environments, nature can produce stability and precision. They remind us that the universe is not only violent and unpredictable, but also capable of remarkable regularity. These cosmic lighthouses guide our understanding of space, time, and matter, sending steady signals across the galaxy, patiently waiting for curious minds to listen. And as we continue, pulsars will lead us deeper into the heart of neutron stars, helping us explore what lies beneath their surfaces and how matter behaves when pushed beyond all familiar limits. When we look at a neutron star from the outside, we see an object defined by gravity, rotation, and radiation. But the greatest mystery of all lies inside it. What exactly fills the interior of a neutron star? What happens to matter when it is crushed so tightly that atoms no longer exist? These questions take us to the edge of human understanding, where physics becomes uncertain and imagination must work alongside evidence. The inside of a neutron star is one of the few places in the universe where we know something extraordinary is happening, yet we cannot directly observe it. Everything we know comes from theory, indirect measurements, and careful reasoning. At first glance, scientists describe the inside of a neutron star as having layers, much like Earth. But these layers are nothing like rock, water, or molten metal. They are layers of matter under pressures and densities so extreme that familiar words barely apply. Starting from the outside, the neutron star has a crust. This crust is incredibly hard, far stronger than steel. It is made of atomic nuclei packed closely together, surrounded by a sea of electrons. Even here, conditions are already far beyond anything found on Earth. The crust is only a few kilometers thick, but it supports the weight of an entire star, pressing down from above. As we move deeper beneath the surface, the pressure increases rapidly. At some point, the structure of normal atomic nuclei begins to break down. Neutrons start to leak out of nuclei and move freely. This region marks the transition from the crust to the outer core. Here, matter is no longer made of individual atoms. Instead, it becomes what scientists often call a neutron soup. Neutrons dominate, moving freely in an incredibly dense environment, mixed with a small number of protons and electrons. The word soup is not meant to suggest anything liquid or warm in the everyday sense. It simply means that particles are no longer locked into rigid structures. They flow and interact under extreme conditions. In the outer core, gravity and quantum physics work together in ways that feel almost contradictory. Neutrons are squeezed tightly together, yet they cannot collapse completely because of fundamental quantum rules. These rules prevent identical particles from occupying the same state. This resistance is what helps support the neutron star against further collapse. The outer core contains most of the star's mass, and its behavior determines many of the neutron star's observable properties, such as how it spins and how it responds to internal stress. Going deeper still brings us to the greatest mystery: the inner core. This region exists at densities several times higher than that of an atomic nucleus. At these pressures, even neutrons may not remain intact, and this is where certainty ends. Scientists do not know exactly what matter looks like in the inner core of a neutron star. They have ideas, models, and competing theories, but no direct confirmation. One possibility is that the inner core is simply a more extreme version of neutron soup, where neutrons are packed even tighter together. Another possibility is far more exotic. Some theories suggest that neutrons may break down into their fundamental components, called quarks. If this happens, the core could be filled with quark matter, a dense state where quarks move freely instead of being locked inside neutrons and protons. This kind of matter has never been observed directly anywhere in the universe. There are even more unusual ideas. Some models predict the presence of particles called hyperons, heavier cousins of neutrons and protons. Others suggest strange matter, containing particles with properties unlike anything found in normal atoms. In the most speculative theories, the core could be something entirely unknown, a state of matter that physics has not yet named. What makes this mystery so difficult is that neutron stars sit in a regime where two major areas of physics collide. On one side is quantum physics, which governs the behavior of particles at very small scales. On the other side is gravity, described by Einstein's theory of relativity. Both theories work extremely well in their own domains, but combining them under extreme conditions is one of the greatest challenges in science. Inside a neutron star, both effects are strong at the same time. Our equations become uncertain. Our predictions diverge. We cannot drill into a neutron star. We cannot sample its material. We cannot recreate its core conditions on Earth. Even the most powerful particle accelerators fall far short of the pressures found inside these objects. As a result, scientists must rely on indirect clues. They study how neutron stars spin, how they vibrate, how they cool over time, and how they behave when they collide. These observations place limits on what the interior can be like, but they do not provide a complete picture. For example, the maximum possible mass of a neutron star depends on what is happening in its core. Some types of exotic matter would make neutron stars softer and easier to compress, limiting their maximum mass. Others would make them stiffer and more resistant to collapse. By observing very massive neutron stars, scientists can rule out certain theories and support others. This is how progress is made, slowly and carefully. Neutron star collisions have also provided new insights. When two neutron stars merge, the way they deform and emit gravitational waves depends on their internal structure. These signals carry information about the stiffness of neutron star matter. Even so, interpreting these signals is extremely complex, and many possibilities remain open. The uncertainty surrounding neutron star cores is not a failure of science. It is a sign of how far we have pushed our understanding. We are studying matter under conditions that existed only moments after the Big Bang. In a sense, neutron stars are time capsules, preserving extreme states of matter that no longer exist elsewhere in the universe. This is where the limits of human knowledge become clear. We know enough to say that the interior of a neutron star is unlike anything on Earth. We know enough to model its behavior and predict its effects, but we do not yet know the full truth. There may be surprises waiting inside these stars, forms of matter that challenge our deepest assumptions. That uncertainty is not something to fear, it is something to celebrate. Neutron stars remind us that the universe is still full of unanswered questions. Even with all our technology and theories, nature continues to hold secrets. The core of a neutron star is one of those secrets, a place where physics reaches its breaking point, and new understanding waits just beyond our reach. As we move forward, this hidden interior will continue to influence everything a neutron star does. Its internal structure affects how it spins, how it glitches, how it emits radiation, and how it responds to stress. By studying neutron stars, we are not just learning about dead stars, we are learning about the fundamental nature of matter itself, tested under the most extreme conditions the universe can offer. Neutron stars and black holes are often mentioned together, as if they are close relatives, and in many ways they are. Both are born from the deaths of massive stars. Both are shaped almost entirely by gravity. Both push physics to its limits. Yet despite these similarities, neutron stars and black holes are fundamentally different objects, separated by a thin but critical boundary in nature. Understanding the difference between them helps us understand where the universe draws the line between something that still exists and something that disappears forever. Let's start with the most basic idea. A neutron star is a real physical object with a surface. It has size, structure, and matter you can describe, even if that matter is extremely strange. A black hole, on the other hand, is not an object in the usual sense. It is a region of space where gravity has become so strong that nothing, not even light, can escape. The difference between these two outcomes comes down to one thing: mass. When a massive star dies, its core collapses. If the remaining core is within a certain mass range, gravity compresses it into a neutron star and then stops. If the core is slightly more massive, gravity never stops. The collapse continues without limit, forming a black hole. This makes neutron stars and black holes cosmic neighbours, separated by a narrow margin. A small difference in mass decides whether matter survives in an extreme form or vanishes behind an invisible boundary. In terms of size, neutron stars and black holes are both incredibly small compared to normal stars. A typical neutron star is about 20 kilometers wide, roughly the size of a city. A black hole formed from a stellar collapse can be even smaller in terms of the region from which light cannot escape, called the event horizon. For some black holes, this region can be only a few kilometers across, but this similarity in size is misleading. A neutron star is small because matter is compressed. A black hole is small because space itself has collapsed. Gravity is extreme in both cases, but it behaves differently. On a neutron star, gravity is incredibly strong, but finite. You can calculate it. You can stand at a certain distance and measure how gravity changes. Light is bent, time is slowed, but escape is still possible if you have enough energy. On a black hole, gravity becomes absolute at the event horizon. Once something crosses that boundary, escape is impossible. There is no force in the universe that can pull it back out. This brings us to one of the most important differences: surface versus event horizon. A neutron star has a solid surface. If matter falls onto it, that matter crashes into the surface at incredible speed. The impact releases enormous energy in the form of heat, X-rays and gamma rays. This is why neutron stars can be incredibly bright in certain wavelengths. Matter hits something solid and releases its energy violently. A black hole has no surface. Instead, it has an event horizon. This is not a physical wall, it is a boundary in space-time. Matter falling into a black hole does not crash into anything. From the outside, it appears to slow down and fade as it approaches the event horizon. Once it crosses that boundary, it is gone forever, hidden from the rest of the universe. There is no impact, no surface explosion, no direct signal telling us what happens next. The difference becomes even clearer when we ask a simple question: what happens when matter falls in? Imagine gas drifting toward a neutron star. As it falls, it accelerates rapidly due to gravity. By the time it reaches the surface, it is moving at a significant fraction of the speed of light. When it hits the surface, all that energy is released in a violent burst. This makes neutron stars powerful sources of radiation, especially when they're feeding on material from a nearby companion star. Now imagine the same gas falling toward a black hole. As it falls, it also accelerates and heats up. This process can release enormous energy before the gas reaches the event horizon. But once it crosses that boundary, the story ends. No signal comes back out. The black hole does not glow from a surface impact because there is no surface. The energy simply disappears from view. In this sense, neutron stars are often more active and dramatic than black holes. They flash, pulse, burst and quake. They have surfaces that crack. They have magnetic fields that snap and release energy. Black holes, by contrast, are often quiet. They reveal themselves mainly through their influence on nearby matter. They are extreme, but in a silent, hidden way. So which one is more extreme? The answer depends on what we mean by extreme. In terms of gravity, black holes win. Nothing beats a black hole's ability to trap light and erase information from the observable universe. The event horizon represents a point of no return, something no neutron star can match. But in terms of matter, neutron stars are arguably more extreme. They contain matter in a state that exists nowhere else in the universe. They allow us to study physics at nuclear densities, to observe how matter behaves under conditions we cannot recreate on Earth. A black hole hides its interior completely. A neutron star exposes its physics through radiation, rotation, and vibration. In this way, neutron stars give us more information. Another key difference is stability. A neutron star exists in a delicate balance. Gravity is pushing inward, while quantum forces are pushing outward. This balance can last for billions of years, but it is not guaranteed forever. Add a little more mass and the balance breaks. The neutron star collapses into a black hole. A black hole, once formed, is stable in a different way. It does not resist gravity, it is gravity. Neutron stars also allow us to test fundamental theories directly. Their pulses test relativity. Their mergers produce gravitational waves. Their interiors challenge nuclear physics. Black holes also test relativity, but mostly through their effects on spacetime outside the event horizon. The most interesting part of a black hole remains hidden. To picture the difference clearly, imagine two cosmic pits. One pit has a solid bottom. If you fall in, you hit something hard, releasing a violent burst of energy. That pit is a neutron star. The other pit has no bottom at all. Once you fall past a certain point, you are gone forever. That pit is a black hole. Both are terrifying. Both are extreme. But they represent different outcomes of the same cosmic process. Neutron stars and black holes show us the two final fates of massive stars. One becomes a city-sized object, packed with matter so dense it breaks our intuition. The other becomes a region of space where reality itself collapses inward. One leaves behind something we can study directly. The other hides its deepest secrets forever. Understanding the difference between neutron stars and black holes helps us understand the limits of nature. It shows us how finely balanced the universe is, how a small difference in mass can decide between survival and disappearance. Neutron stars sit at the edge, the last place where matter can exist before gravity erases it completely. And that is what makes neutron stars so special. They are the final stand of matter against gravity, the most extreme objects that still allow us to see, measure, and learn. For most of their lives, neutron stars are solitary, silent objects, spinning quietly in the darkness of space. But sometimes, fate places two of them together. Bound by gravity, they begin a long, slow dance that will eventually end in one of the most violent events the universe can produce. When two neutron stars collide, the universe itself shakes, space ripples, time vibrates, matter is torn apart and reborn. These collisions are not just dramatic endings, they are cosmic creation events, responsible for some of the most precious elements on Earth, including the gold in your jewelry. A binary neutron star system forms when two massive stars are born close together. These stars live fast and die young. Each one explodes in a supernova, leaving behind a neutron star. If the system survives both explosions without being torn apart, the two neutron stars remain locked in orbit around each other. At first, they may orbit peacefully, separated by millions of kilometers. But gravity is patient. Over millions or even billions of years, the orbit slowly shrinks. This slow inward spiral happens because the system is losing energy. The energy is not lost through light or heat. It is lost through something far stranger: gravitational waves. These are ripples in space-time itself, predicted by Einstein and confirmed only recently. As the neutron stars orbit each other, their enormous mass and rapid motion disturb the fabric of space-time, sending out waves that carry energy away. Each wave steals a tiny amount of orbital energy, pulling the stars closer together. At first, this process is gentle and slow. The neutron stars orbit each other calmly, like two dancers far apart on a floor. But as the distance between them decreases, everything speeds up. The orbits become tighter, the stars move faster, gravitational waves grow stronger. In the final moments, the neutron stars can orbit each other hundreds of times per second. The universe prepares for impact. When the collision finally happens, it is sudden and catastrophic. The neutron stars slam into each other at incredible speed, releasing an unimaginable amount of energy in a fraction of a second. Their intense gravity tears matter apart, stretching and squeezing it violently. The stars deform, merge, and collapse into a single object. Depending on the total mass, the result may be a larger neutron star or a newly formed black hole. During the collision, space-time itself shakes violently. This shaking spreads outward as gravitational waves, traveling across the universe at the speed of light. By the time these waves reach Earth, they are incredibly weak, but sensitive detectors can still measure them. In 2017, scientists detected gravitational waves from a neutron star collision for the first time. This event confirmed decades of theory and opened an entirely new way of observing the universe. Gravitational waves are difficult to imagine because they are not waves in space. They are waves of space. As they pass through Earth, they slightly stretch and squeeze everything they touch, including the detectors designed to measure them. These changes are smaller than the width of an atom, yet they carry clear information about the event that caused them. From these signals, scientists can determine the masses of the neutron stars, the speed of the collision, and even clues about their internal structure. But the shaking of the universe is only part of the story. Neutron star collisions are also factories of matter. During the collision, enormous amounts of neutron-rich material are thrown into space. In this violent environment, atomic nuclei rapidly capture neutrons, building heavier and heavier elements. This process, known as rapid neutron capture, creates elements that cannot be formed inside normal stars. This is where the story becomes personal. Gold, platinum, and many other heavy elements are not produced in ordinary stellar fusion. They require extreme conditions. Neutron star collisions provide exactly that. In a single collision, enough gold can be created to form entire planets. The material blasted into space spreads out, mixing with gas clouds that later form new stars and planets. Every ring, necklace, and electronic circuit containing gold carries a hidden cosmic history. The atoms inside were forged not in peaceful stars, but in the violent collision of two neutron stars billions of years ago. When you hold gold in your hand, you're holding the aftermath of a cosmic catastrophe. These collisions also produce powerful bursts of light, including gamma rays, X-rays, and visible light. For a brief time, the collision can shine brighter than an entire galaxy. This glow, called a kilonova, fades over days and weeks as radioactive elements decay. Observing these flashes alongside gravitational waves allows scientists to study the event from multiple perspectives, combining light and gravity into a single picture. Neutron star collisions teach us something profound about the universe. They show that destruction and creation are deeply connected. The same event that tears stars apart also builds the elements needed for planets, technology, and life. Violence on a cosmic scale becomes the source of beauty and value on a human scale. These events also help scientists test the laws of physics under extreme conditions. By studying how neutron stars deform and merge, researchers learn about the stiffness of neutron star matter and the behavior of gravity in its strongest form. Each collision is a natural experiment conducted by the universe itself. To visualize a neutron star collision, imagine two city-sized objects, each heavier than the sun, spiraling toward each other faster and faster. Space around them trembles. Time stretches. When they finally collide, the energy released rivals the power of all the stars in the galaxy combined, if only for a moment. The universe shakes, and new matter is born. Neutron star collisions remind us that the universe is not static or gentle. It is dynamic, creative, and sometimes violent. Yet from that violence comes everything we value. The elements that make our world solid, colourful, and conductive were forged in events like these. When we study neutron star collisions, we are not just studying distant explosions, we are studying our own origins. We are learning where the building blocks of our world came from. The next time you see gold shining in sunlight, remember that it was born in a moment when the universe itself trembled. Neutron stars are among the most extreme objects in the universe, yet they are also some of the hardest to find. They are small, dark, and distant. They do not shine brightly like normal stars, and most of them are completely invisible to the human eye. And yet scientists have discovered thousands of neutron stars scattered across our galaxy. How is this possible? How do we detect objects that are city-sized, often billions of kilometers away, and hidden in the darkness of space? The answer lies in using the universe's own signals and building instruments sensitive enough to listen, rather than simply look. The first and most important tool used to detect neutron stars is the radio telescope. Unlike optical telescopes, which collect visible light, radio telescopes detect radio waves. Radio waves are a form of light, but with much longer wavelengths than what our eyes can see. Many neutron stars, especially pulsars, emit strong radio signals as they spin. These signals travel through space for thousands or even millions of years, crossing gas clouds and dust that would block visible light until they finally reach Earth. Radio telescopes work by collecting these faint radio signals using large dish-shaped antennas. The larger the dish, the more signal it can collect. Some radio telescopes are single massive dishes, while others are networks of many antennas spread across large distances. These networks work together as one giant telescope, allowing scientists to pinpoint the exact location of a neutron star and study its signals in detail. When a radio telescope detects a repeating pulse with precise timing, scientists immediately pay attention. This regular pulsing is a strong signature of a pulsar, a rotating neutron star with beams of radiation sweeping through space. By analysing the timing of these pulses, scientists can determine how fast the neutron star is spinning, how it is slowing down, and even whether it has a companion star. Radio telescopes turn neutron stars from theoretical ideas into observable objects. However, not all neutron stars are radio pulsars. Some are silent in radio wavelengths or beam their signals away from Earth. To find these hidden neutron stars, scientists use X-ray and gamma-ray detectors. Neutron stars are incredibly hot when they are young, and even older ones can emit X-rays due to their strong magnetic fields and intense gravity. When matter falls onto a neutron star from a companion star, it heats up dramatically, glowing brightly in X-rays before crashing onto the surface. X-rays and gamma rays cannot be detected from the ground because Earth's atmosphere blocks them. This is a good thing for life, but it means scientists must place detectors in space. Space telescopes equipped with X-ray and gamma-ray instruments orbit above Earth's atmosphere, scanning the sky for high-energy signals. These telescopes have revealed neutron stars that would otherwise remain invisible. Gamma-ray telescopes have been especially important in discovering magnetars and high-energy pulsars. These objects emit bursts of extremely energetic radiation that can briefly outshine entire galaxies. By tracking these bursts, scientists can identify neutron stars even when they are not emitting regular pulses. One of the biggest challenges in detecting neutron stars is that we cannot see them with our eyes. Neutron stars are too small and too faint in visible light. Even the closest neutron stars appear as tiny dim points, completely lost among billions of stars. Their visible light is weak because they no longer produce energy through fusion. Any light they emit comes from leftover heat or high-energy processes, not from steady burning like the sun. This limitation forces astronomers to rely on indirect evidence. Instead of seeing neutron stars directly, They observe the effects neutron stars have on their surroundings. They study how they pulse, how they pull material from companion stars, how they bend light, and how they disturb spacetime itself. Neutron stars reveal themselves through their influence, not their appearance. Some of the most famous discoveries in astronomy involve neutron stars. The discovery of pulsars in 1967 completely changed our understanding of stellar death. The first detection of a neutron star collision through gravitational waves in 2017 confirmed decades of theoretical predictions. Observations of extremely massive neutron stars have ruled out entire classes of theories about the nature of dense matter. Another important method of detecting neutron stars involves studying binary systems. When a neutron star orbits another star, its strong gravity can pull material from its companion. This material forms a swirling disk around the neutron star, heating up and emitting X-rays. By observing these X-ray binaries, scientists can identify neutron stars even when they are not pulsing. Modern astronomy relies heavily on space missions designed specifically to study high-energy phenomena. Satellites such as X-ray observatories and gamma-ray telescopes constantly scan the sky, watching for bursts, pulses, and flashes. Radio observatories on Earth continue to discover new pulsars, including some spinning hundreds of times per second. Together, these instruments create a multi-layered view of neutron stars across the electromagnetic spectrum. In recent years, scientists have added a completely new tool to their detection methods: gravitational wave observatories. These detectors do not look for light at all. Instead, they measure tiny distortions in spacetime caused by massive objects moving rapidly. When two neutron stars collide, they send out gravitational waves that ripple across the universe. By detecting these ripples, scientists can identify neutron star mergers even if no light is visible. What makes neutron star detection so powerful today is the combination of methods. Scientists no longer rely on a single signal. They combine radio waves, X-rays, gamma rays, visible light, and gravitational waves to build a complete picture. This approach is called multi-messenger astronomy, and neutron stars are at the heart of it. Detecting neutron stars is a triumph of human ingenuity. These objects are tiny on cosmic scales, invisible to our eyes and often hidden behind dust and distance. Yet by listening to the universe, instead of just looking at it, scientists have learned to find them. Every pulse detected, every burst recorded, and every gravitational wave measured adds another piece to the puzzle. Neutron stars remind us that the universe speaks in many languages. Some messages arrive as light, others arrive as radio waves or ripples in spacetime. To understand the universe, we must learn to listen carefully, and by doing so, we have uncovered some of the most extreme objects nature has ever created. As our instruments grow more sensitive and our missions more ambitious, the number of known neutron stars will continue to rise. Each new discovery brings us closer to understanding how matter, gravity, and energy behave at their limits. And with every detection, we prove that even the darkest and most distant corners of the universe are within reach of human curiosity and persistence. The idea of life near a neutron star immediately sparks the imagination. Science fiction often paints dramatic pictures of strange beings living under alien skies, surviving near powerful cosmic objects. But when we move from fiction to real physics, the question becomes far more serious and far more unsettling. Could life exist near one of the most extreme objects in the universe? To answer this, we must confront just how hostile the environment around a neutron star truly is, and then carefully separate what science allows from what stories invent. A neutron star is not just extreme in one way, it is extreme in every possible way at once. Gravity is crushing, radiation is intense, magnetic fields are deadly, and stability is rare. Even far from the surface, conditions remain hostile. Unlike a normal star, which provides light and warmth at safe distances, a neutron star is dangerous almost everywhere around it. There is no comfortable zone where conditions gently fade into safety. Instead, danger decreases slowly and unevenly, stretching far into space. Gravity alone makes life near a neutron star almost impossible. The gravitational pull is so strong that even at great distances, it can distort orbits and tear objects apart. Any planet attempting to orbit a neutron star would face enormous challenges. Orbits would need to be perfectly balanced. A small disturbance could send the planet crashing inward or flinging outward into space. Tidal forces would stretch and squeeze the planet, heating it internally and possibly ripping its crust apart. On Earth, tidal forces cause ocean tides. Near a neutron star, tidal forces could crack continents. Radiation is an even greater threat. Neutron stars emit powerful radiation across the electromagnetic spectrum, including X-rays and gamma rays. These forms of radiation are extremely dangerous to life as we know it. They damage DNA, destroy cells, and strip away atmospheres. A planet close enough to receive energy from a neutron star would also receive lethal radiation. Unlike sunlight, which is relatively gentle and stable, neutron star radiation is harsh, unpredictable, and often explosive. Many neutron stars emit intense beams of radiation as they rotate, especially pulsars. These beams sweep through space like rotating blades. If a planet's orbit crossed one of these beams, it would be regularly bombarded with bursts of high-energy radiation. Each pass could sterilize large portions of the surface. Over time, this radiation would likely remove any atmosphere entirely, leaving the planet exposed and barren. Magnetic fields add another layer of danger. Near Magnetars, the strongest type of neutron stars, magnetic fields are powerful enough to disrupt atoms. Any nearby matter would be affected at a fundamental level. Even electronics on spacecraft would fail long before reaching such environments. For life, this level of magnetic stress would be fatal. It would interfere with chemical bonds and biological processes, making stable biology impossible. Then there is the problem of energy stability, which is essential for life. Life requires a steady energy source over long periods of time. Neutron stars are not steady providers. Their energy output can change suddenly and violently. Starquakes, magnetic flares, and bursts of radiation can occur without warning. These events release enormous energy in seconds. Any life nearby would face repeated extinction-level events. Because of these dangers, most scientists agree that life, as we know it, cannot exist near a neutron star. No Earth-like biology could survive the gravity, radiation, and instability. Even extremophiles, organisms on Earth that survive extreme heat, pressure, or radiation, would not stand a chance under such conditions. The environment is not just harsh, it is fundamentally incompatible with biological chemistry. However, this is where science becomes fascinating rather than dismissive. While life near neutron stars is extremely unlikely, it is not meaningless to ask the question. Asking whether life could exist there forces us to examine our assumptions about life itself. Are we too focused on Earth-like conditions? Are there forms of life that do not rely on liquid water, stable atmospheres, or gentle radiation? Some scientists speculate about exotic forms of life, not based on chemistry as we know it, but on entirely different principles. These ideas are highly speculative and remain firmly in the realm of theory. But neutron stars challenge us to consider whether life could exist in forms we cannot yet imagine, perhaps based on nuclear processes, magnetic structures, or unknown states of matter. Science fiction often takes these ideas much further. Stories imagine civilizations harnessing neutron star energy, living on artificial structures nearby, or even inhabiting the star itself. These ideas are creative and entertaining, but they ignore key physical realities. Any structure near a neutron star would face immense tidal forces and radiation damage. No known material could survive long-term exposure. While advanced technology might offer temporary protection, permanent habitats remain unrealistic. Still, neutron stars may play an indirect role in life. They are not places where life lives, but places where life's ingredients are created. Neutron star collisions produce heavy elements like gold, platinum, and uranium. These elements become part of planets, chemistry, and biology elsewhere in the universe. In this sense, neutron stars contribute to life without hosting it. There is also the intriguing possibility of life existing far from a neutron star, not near its surface but at safe distances. Some neutron stars have planets orbiting them, discovered through pulsar timing. These planets likely formed after the supernova explosion from leftover material. Even so, these environments are still extremely challenging, and no evidence suggests they are habitable. But their existence shows that neutron stars are not completely isolated from planetary systems. What makes the question of life near neutron stars so powerful is not the answer, but the perspective it offers. Neutron stars represent the far edge of habitability, the point where nature becomes too extreme for life as we understand it. They remind us that the universe is not designed for comfort. Life exists only in narrow windows of stability, surrounded by vast regions of hostility. Thinking about life near neutron stars also sharpens our understanding of what makes Earth special. Our planet sits in a calm orbit around a stable star, protected by a magnetic field and atmosphere. The contrast with neutron stars highlights just how rare and fragile habitable conditions may be. In the end, neutron stars are unlikely homes for life, but they are powerful teachers. They show us the boundaries of biology and physics. They push us to question what life really needs and where it can exist. They remind us that while the universe is full of wonders, not all wonders are welcoming. The fascination lies in that tension. Neutron stars are beautiful, terrifying, and mysterious. They are places where life almost certainly cannot survive, yet they force us to think more deeply about life itself. And sometimes the most important scientific questions are not about where life exists, but about why it exists at all, and how narrow the path to survival truly is in a universe this extreme. Neutron stars matter to us not because they threaten Earth or because we will ever visit them, but because they reveal something essential about the universe and about ourselves. They are reminders that reality is far stranger, deeper, and more powerful than everyday experience suggests. When we study neutron stars, we are not just studying dead stars. We are studying the limits of nature, the boundaries of matter, and the rules that govern everything that exists, including us. At their core, neutron stars teach us about physics under extreme conditions. On Earth, we test physical laws in laboratories, using particles, magnets, and carefully controlled experiments. But there are limits to what we can build. We cannot compress matter to nuclear density. We cannot create gravity strong enough to bend light significantly. We cannot slow time in a measurable way. Neutron stars do all of this naturally. They are cosmic laboratories, created by the universe itself, running experiments we could never perform. By observing them, we learn how matter behaves when pushed far beyond familiar conditions. One of the most important lessons neutron stars teach us is about gravity. Einstein's theory of relativity describes gravity not as a force, but as the bending of space and time. On Earth, these effects are tiny. Near neutron stars, they are impossible to ignore. Light curves, time slows, orbits shift. By studying pulsars and neutron star binaries, scientists can test Einstein's ideas with incredible precision. So far, his predictions have held up astonishingly well, even under these extreme conditions. Each neutron star observed is another test passed, another confirmation that our understanding of gravity reaches far beyond everyday life. But neutron stars also reveal where our knowledge begins to struggle. Their interiors push physics to its breaking point. Inside them, quantum mechanics and gravity collide in ways we still do not fully understand. The uncertainty surrounding their cause is not a weakness of science. It is a sign that we are standing at the edge of discovery. Neutron stars show us where new theories are needed, where deeper understanding waits just beyond what we currently know. Understanding extremes matters because the universe itself is built from extremes. Stars live and die, matter forms and collapses. Energy flows, sometimes gently, sometimes violently. Neutron stars are not rare accidents. They are a natural outcome of stellar evolution. By understanding them, we understand a fundamental chapter of the universe's story. We learn how elements are formed, how galaxies evolve, and how the building blocks of planets and life are created and scattered across space. There is also a deeply human reason neutron stars matter. They give us perspective. When we compare our world to a city-sized object heavier than the sun, spinning hundreds of times per second, wrapped in gravity and magnetism that can tear atoms apart, our everyday worries shrink. This is not meant to diminish human experience, but to place it in context. We live on a small planet, orbiting an ordinary star, in a calm corner of a vast and often violent universe. That calm is precious. Neutron stars remind us how narrow the conditions for life truly are. They show us what happens when nature steps outside that narrow window. In doing so, they highlight how remarkable it is that we exist at all. The fact that we can study neutron stars, that we can understand them, even partially, is itself extraordinary. The universe produced not only neutron stars, but also minds capable of asking what they are. There is also wonder in the idea that the same laws governing neutron stars govern us. The atoms in your body obey the same physics as the matter crushed inside a neutron star. The gold on Earth was forged in neutron star collisions. The calcium in your bones was scattered by ancient stellar explosions. In a very real sense, neutron stars are part of our history. They are distant, extreme, and dangerous, yet connected to us through the chain of cosmic events that made life possible. Importantly, neutron stars do not invite fear. They are not threats lurking in space. They are far away, rare, and mostly silent. Their value lies not in danger, but in insight. They show us that the universe is capable of both immense violence and astonishing order. From supernova chaos comes pulsar precision. From collapse comes structure. From destruction comes creation. As we reach the end of this journey, neutron stars stand as symbols of the universe's depth. They show us that reality is layered, that beneath the surface of what we see lies something far more complex. They encourage humility, curiosity, and patience. Every generation learns a little more. Every observation adds a piece to the puzzle. We may never fully understand what lies at the core of a neutron star. We may never recreate its conditions, but that does not lessen its importance. Some mysteries are valuable precisely because they remain open. They remind us that science is not a finished book, but an ongoing conversation between humanity and the universe. In the end, neutron stars matter because they expand our sense of what is possible. They stretch our imagination without breaking it. They show us that the universe is not simple, not gentle, and not designed for comfort. Yet it is deeply ordered and profoundly beautiful. We are small. Our planet is small. Our time is brief. But our curiosity reaches across galaxies. When we look at neutron stars, we are not looking for fear or meaning imposed from outside. We are looking for understanding. And in that search, we find something powerful. A reminder that even in a universe filled with extremes, we belong. Not because we are strong, but because we are capable of wonder. At the beginning of this journey, we imagined something impossible. We imagined crushing a mountain into a sugar cube and still not reaching the density of a neutron star. That idea felt unreal then, and it should still feel unreal now. Because neutron stars exist in a part of reality that our minds were never designed to fully grasp. And yet, they are real. They are out there right now, scattered across the galaxy, silent and spinning, carrying the memory of stars that lived fast and died violently. Along the way, we saw how familiar ideas break down. Size no longer matches weight. Time no longer flows evenly. Light bends. Matter forgets what it used to be. Neutron stars show us that the universe is not obligated to make sense to human intuition. Reality is far stranger than our everyday experience suggests, and far more extreme than our language can comfortably describe. But this strangeness is not something to fear. It is something to wonder at. Neutron stars remind us that knowledge is not about comfort. It is about curiosity. Every time we push our understanding forward, we discover that the universe is deeper than we expected. And instead of closing doors, those discoveries open new ones. Think about what it means that we can even ask these questions. We live on a small planet, orbiting an ordinary star in a quiet corner of space. And yet, from here, we can detect the ticking of pulsars across the galaxy. We can measure ripples in space-time caused by neutron star collisions. We can trace the gold in our hands back to cosmic violence billions of years ago. The universe is vast and indifferent, but it has produced minds capable of understanding it. This is why learning matters. Not because every mystery must be solved, but because each mystery expands our sense of reality. Neutron stars may never become familiar. They may always feel alien, and that is exactly why they are important. They remind us that the universe is bigger than our habits, our fears, and our assumptions. So don't let this be the end. Let it be a pause. A quiet moment to sit with the idea that reality is far stranger and more beautiful than it appears at first glance. Let curiosity linger. Let questions remain unanswered. Because the universe does not reward certainty, it rewards wonder. The neutron stars will keep spinning long after this video ends. And the next time you look up at the night sky, remember that somewhere in that darkness, city-sized stars heavier than the sun are quietly bending space and time. You don't have to fully understand them to be changed by them. Sometimes, it's enough to simply know that they exist.